now let's look at higher order partial derivatives. The notation for taking the partial derivative of a partial derivative. So first we find the partial of f with respect to x. Then we take the partial of this with respect to x again, and the notation becomes the second partial of f with respect to x. And this is the notation. Very similar to when we were doing just derivatives. The derivative of a derivative with respect to x was just the second derivative of y with respect to x. So similar notation here. Using this other notation with the subscripts, this is what's done first, the partial with respect to x, and then you take the partial with respect to x of that. And so when you see this notation without any parentheses, the one closest to the f is done first. And this is the second thing. So you could say it's d squared f dx squared, which I won't ever say that, or you can say f sub x x here, or you can just say the partial derivative of f with respect to x twice. F sub xx is probably what I would say for the second partial. Now here, using this differential notation, you first are finding the partial of f with respect to y, and now you're going to take the derivative with respect to y again. And so this is the notation, or here you're doing the partial with respect to y first, and then the partial with respect to y. And then in this notation, the one first is the one closest to the f. Okay, and the differential notation, it wasn't the one closest to the f, it was whatever was the second thing following that differential notation. So now, when you're mixing them is when it's going to be more confusing. You first find the partial with respect to y, and then with respect to x. So now notice that this differential notation will have them in the order that it would be written with this notation, but the one done first is the one on the right. So you do the partial with respect to y first, and then the partial with respect to x. So down here, it would be the partial with respect to x first, and then the partial with respect to y. But in this other notation, the subscripted notation, you're doing the partial with respect to x first, which is the first one. So be aware of that. So this would be f sub x y, and this one would be f sub y x. In this notation, the one furthest to the right is done first, but in this notation, the one closest to the f is done first. Now to evaluate at a point, the different notation that we'll use will be just the partial of f with respect to x at a point AB, or we can write it with the vertical bar like we did in the previous example and just put the point down here. We don't need to say x equal because it's an xy value, so just indicate the point down there. Or the simplest looking notation is to have that partial with respect to x and indicate the point following that. So now let's find the 4 second partial derivatives of this function. The first partial derivatives would be f sub x. So we're taking the partial with respect to x, meaning that the y is going to be a constant. So in the derivative, you will take the derivative of these 3 terms and then add or subtract them using the sum rule. So the partial of 3x to the 4th times y, since y is just a constant, these are both just constants. So we'll have the constants, 3y, times the derivative of the x to the 4th. Now minus the 2xy, the 2 and the y are constants, so minus 2y, and now the derivative of the x, which is just 1. In the last one, the constant is just 5y cubed, and now the derivative of the x, which is just 1. So the first partial with respect to x is 12x cubed y minus 2y plus 5y cubed. Now, let's find the partial of f with respect to y. Here, our x is constant. Again, we start with our sum rule. So we'll be taking the derivative of these three terms separately and adding or subtracting them. The derivative of 3x to the fourth y, if x is a constant, this whole thing is a constant. So the constant times the derivative of the y, which is 1. Minus, now the x is constant, so minus 2x is all constant, and times the derivative of the y, which again is 1. X is constant, so this is all a constant, times the derivative of y cubed is 3y squared. So we have 3x to the fourth minus 2x plus 15xy squared. So now, we've got the partial with respect to x. Now let's find the partial of that with respect to y. So we're going to find f sub x y we're taking the derivative of this, but now with respect to y. So our x's are all constant. So we'll have 12x cubed times the derivative of y minus 2 times the derivative of y plus the derivative of 5y cubed with respect to y is 15y squared. Now let's take the partial of f sub x x. So we already took the partial with respect to x, and we'll do it again with respect to x. So now the constant is 12y times the derivative of x cubed is 3x squared minus 2 times the derivative of y, which is just 0 since y is a constant. And then y is a constant, so that's 5 times the derivative of y cubed, which is 0 again. So that's the second derivative of f with respect to x, or f sub xx. Now, let's find the partial of f with respect to y again. So we're taking the derivative of this with respect to y. X is a constant. So the derivative of 3x to the fourth is 0. The derivative of minus 2x is 0. The derivative of this, x is a constant, so I'll have 15x times the derivative of y squared is 2y. And finally, the partial with respect to y first, and then the derivative of that with respect to x. So now our y is the constant. So we're taking the derivative of this function with respect to x. It'll be 12x cubed minus 2. Y is a constant, so it's 15y squared times the derivative of x. Now you might notice here that the partial of f with respect to xy, f sub xy, is the same as the partial of f with respect to yx. That will be the case most of the time in this class. In order for those two partial derivatives to be the same, certain conditions have to be met. And those conditions, assuming f is defined on an open set D inside of R squared, or R2, f sub xy and f sub yx, or if they're both continuous throughout that whole open set, then those two partial derivatives will be the same at all points in that open set D. So if the function is defined on an open set and the two partial derivatives are continuous for that set, then the two partials will be the same. And most of the functions we deal with will have those two partial derivatives continuous, so those will be the same. So it's a good way to check yourself.